take the carbon phase and make it nodular, so it's only balls of carbon-rich phase, and that is ductile iron. So there are ways to make cast iron good in terms of the mechanical properties, but at in the simplest expression, and it's the same with the aluminum alloy, it's not the most ductile alloy that you get. So it's essentially favoring the easy manufacturing as opposed to the best properties. That's really what I want you guys to keep in mind. So that's the aluminum silicon here with the same effect here, about 12% silicon. What happens in solidification, and here I'm drawing some thermodynamics. You don't have to worry too much. I'm not going to get too much in details in it, but essentially you're going for a change in the enthalpy of the material. So exactly how much internal energy your alloy has, and the entropy, which is the organization aspect, because it used to be liquid, things would move all around, and then all of a sudden it's going to be organized as a crystal. So as that effect, you lose a lot of disorganization, so you lose entropy. And that's why overall the reaction is only going to happen in certain very specific conditions. It has to be the easiest thing to happen, to go from the liquid to the solid. It needs to be favored by the phase diagram. And I realize here that I won't be able to go into all the details of these free energy curves, but I will introduce them. So what we're looking at here is that free energy of different phases as a function of composition, and each phase is a curve here. And if I have a material that is this composition here, if I decide to make it only the alpha phase, it's gonna follow that curve, and it will have more energy, or more free energy. If it's going to the liquid, alter the liquid, it will also be higher in the curve, it'll be right up here, so it's more energy. So that's the reason why the easiest state to be is to split into a solid and a liquid. And that's a way, if you one day want to build phase diagram, which people still do today with more advanced technique than back when they did the iron and carbon phase diagram. But it's what you need to look at. You need to look at the free energy and where is your composition, and then the material by itself, if you're cooling down slowly, and we'll talk about that later in the class, is going to distribute itself, so overall it has less free energy. Now, what happens then, if one says, oh, I want to be liquid, I want to be solid, if you have an overall composition, you're going to push away the alloying element to solidify. And that means that right ahead, if I'm the material, if I'm the material just like here in a plane, so I have the solid and the liquid. Every alloying element, say silicon in aluminum, so this is aluminum almost pure. It's pushing the silicon ahead of the solidification front. And what happens is, if I manage to get the silicon into an area here, then I can grow my dendrites, we call, next to it. And that's going to be a lesser concentration of silicon. So now I push the silicon all the way here. So it's a faster way to extrude out, diffuse is the proper term, the silicon. That's why nature wants to do it. And I want to elaborate more on this, but this is the general introduction. This is going to be on Monday. Heat transfer is something that is very, very important in castings. Because you do want to get the heat out. That's the only way you're going to cool. And if you manage to cool faster, all these things about trying to get the silicon here, doing all of that, is harder to do. So if you manage to freeze the liquid, you're eliminating a lot of that diffusion process. So I'm giving an example here of a strip caster where instead of forming that huge billet, you form a thin sheet. And that would be the case for making aluminum foil, for example. What happens here is it's a free surface. You have liquid metal touching two rolls that are going like this, and you're producing down, these rolls are cooled, and you're producing down here that strip of solidified metal. So there's really not much that holds, when you solidify, there's not much that's holding that metal to the roll. And that's one of the problems in terms of heat transfer, because you probably see a lot of things when you cool things down quickly, you have distortion. And the distortion is preventing to keep that good match between the roller surface and what you're trying to solidify. So here, there was a bunch of experiments. I have to skip some of the details. If you're looking here at the back face, so you produce a strip. This is the side that was against the roll, and then this is the side that was in the middle, and then you have another roll here. So these are experiments I did when I was an undergrad, and what we were looking at is essentially just dropping a mold into the molded metal to simulate what happens. So see here, that's the surface. Here you have the first contact, the roller's coming this way, and you're starting to solidify. You build it up, and right here, you're supposed to have the two solids meet to make the strip that you're trying to make. So what you're looking on that image is from here at the surface. And what you see are bumps. The reason you have bumps is there are places where the contact is just a whole lot better between the roller and the mold at others. And you want to try to minimize that. And as it turns out, one way is to have a lot of roughness on your rollers. So you start to form the solid at more locations, and you don't have as much distortion. So the worst here was 2000 is a very fine sanding finish. You have two big bumps. So you can see it when they're going to meet here, you'll have a lot of problem, as opposed to the grit 150, which was you use if you're just going to sand wood, for example. It's relatively coarse in terms when we're talking about sanding metals. So in this case, you have smaller bumps, so you're going to be able to make that merge of the two castings coming together a lot better. So, I mean, there are a lot of things that we could talk about in terms of heat transfer, but this idea that it's varying over time, right? At the very beginning, this is not necessarily all true, because it's very hard with the instrumentation to pick up the heat transfer at the very, very beginning. The instrumentation is behind, but essentially it's very high, and it will reduce over time. The idea there is, if you can keep it under control, you have a better production. There's speed here, but there's also, so we can see with the coarse finish that the heat transfer overall is a little less. But you know, this is what you want. You want something that's rather flat as opposed to something that has the big bumps on it. It's generally the case that you have to think about speed, but also quality. So I managed to do it. That was just an overview in terms of you have to go from the liquid to the solid. You're faced with these differences in composition. The elements want to be pushed away, and they don't want to solidify right away, and that leads to segregation. And in any casting process, heat transfer is important. That's why we do pressure casting. We do a lot of things to try to make sure we get a good and regular transfer of the heat from the mold to the part that we're working on. So we'll cover more solidification, segregation, and I'll talk a little bit about different casting technologies on Monday morning, 8:30. Hope to see you all. Any questions? I mean, it was an introduction. In general, I like if you can interrupt me and sometimes I will also say things that are completely incorrect, and I like to keep it.
There's a question back there.
Yes?
I just have one question of that last slide with the different surface finishes. Is that surface finish of the rollers, essentially?
No, that was this, so you're
Okay, so it's that
looking on
surface
the other
roughness
side.
of the actual,
Yeah, I didn't
okay.
show the, I have a lot of images on the other side, but it's always gonna be relatively plain
Right.
there, because it is touching the roof.
And if some of you haven't signed up, if you drop by my secretary's office and give her your name and address, so. We've obviously got more people here than,